We are Team Visionary, and for our project this year, we have developed a pair of AI glasses that provide real-time text-to-audio transcription to help visually impaired students in education. I'm Akil.
I'm Evan.
And I'm Lucas.
Thomas Edison inspired our project because just like him, we want to create an invention that will change the world for the better. His invention of the light bulb and the electric power system changed the lives of so many people around the world and the future. On the other hand, we want to help visually impaired students learn and gain knowledge, especially in areas where there are few resources.
Existing solutions include Braille. Braille is a tactile writing system used by individuals who are blind or visually impaired. It allows them to read and write by feeling patterns of raised dots arranged in cells, each containing 6 dots arranged in 2 columns of 3 dots each. These patterns represent letters, numbers, punctuation, and even musical or mathematical symbols. Although Braille is an effective way for visually impaired individuals to read material, less than 10% of educational books and writings are converted into a Braille format. Another solution are ePens. ePens scan printed text using optimal character recognition, or OCR technology. The text is then converted into a digital format, which is then read aloud by the device's built-in voice or connected to an external audio output. This solution faces challenges from large or irregular fonts, as the pen might not be able to read or detect the writing, and can provide inaccurate results. Not only is the accuracy a concern, but ePens also take a significant amount of time to convert the text, as they need to process it line by line. On average, it takes around 1 to 3 minutes for an ePen to read a single standard text page. This makes it extremely inconvenient for students needing quick access to their educational material. iReaders are another existing solution. They can scan text with a camera and can take up to a full minute to scan a page of text. Many iReaders are also bulky and not portable, making them an unoptimal solution.
In the United States, approximately 600,000 children face some form of visual impairment, yet less than 7% of educational books are accessible to them in a format of Braille or audio. Braille books, which are a solution, are often large and heavy, making them inconvenient for everyday use. Alarmingly, only 50% of blind students have access to assertive technologies, and just 10 to 50% of blind children know how to read Braille. This lack of accessibility in educational resources contributes significantly to the low graduation rates, with blind students being 80% less likely to graduate compared to their peers. Furthermore, while 85% of visually impaired students are registered in educational programs, only 8% attend specialized residential schools for the blind. As we can see, the majority of visually impaired students don't have access to what they need.
Our solution is a pair of AI-powered glasses that allows visually impaired students to hear text in front of them by converting it into real-time speech. Unlike traditional solutions like Braille books or ePens, these smart glasses use machine learning and object identification to recognize and read text from various surfaces, specializing in school materials and textbooks. They also support multiple languages, translating them into clear, audible speech. With a sleek, lightweight design, our glasses are made to fit students' needs and allows them to succeed in areas with fewer resources.
First, this was a Raspberry Pi 02W used as a microcontroller, and it has Wi-Fi capabilities. The next was a power boost module that increased the voltage of our battery pack. This next item was a jumper wires so we could connect the components of our project. Next, we have a battery pack that has 3.7 volts and 1.1 amps.
Another part we used was the momentary push button, which signaled the microcontroller when to take the picture. Here is another type of push button, which would turn on and off the glasses. Our last component for the glasses was a mini camera, which connected directly to the ports of the Raspberry Pi. One of the materials we used was black PLA filament, which was used to 3D print the glasses frame. Some of the tools we used was a 3D printer, hot glue gun, and a soldering station.
The first step in building our prototype is to print out our custom-designed glasses frame on a 3D printer. We used a Bambu Lab P1P printer. The next step is to solder our 3.7 volt battery to our power boost module. This changes the voltage from 3.7 volts to the voltage needed to power the Raspberry Pi, 5 volts. After this, we soldered our power boost to 2 push buttons, which communicate to the Raspberry Pi when to turn on our prototype and when to start our text to audio transcription. We also soldered the power boost to our Raspberry Pi to give it power. After soldering, we placed all our components in their respective compartments in our glasses frame. And lastly, we attached our camera to the Raspberry Pi and wrapped it around to our glasses lens.
We made the glasses frame and component housing using Fusion 360. Here, we have shown where each component is placed in the glasses.
The image gets taken through the glasses and sent to the API, which then returns the extracted text. Lastly, it is converted into audio and played on the speakers. This was the OCR code we ran, which would run our machine learning model. And finally, this was the code we ran on the glasses to communicate with the API of the OCR code running on the local machine.
The first step in our testing process was to test our software in Python. We uploaded 3 different pictures from educational textbooks and made improvements until our system achieved an accuracy of over 80%. We also tested our software if it can create an MP3 file successfully. Then we tested our physical prototype, seeing if it can read text in different lightings, provide audio, and how accurate it was.
Here is some of the data from our testing, which shows overall positive results.
In conclusion, we developed glasses that scan text, convert it into a text file, transform it into an MP3 file, and broadcast it. The project met all the criteria and constraints, with the OCR system achieving 96% accuracy with flawless audio conversion. Overall, the system proved highly reliable and effective.
After talking to a member from our target audience, they recommended us to add built-in speakers, use smaller parts, add object recognition, and create a model that can run without Wi-Fi.
After gathering all our materials and costs, we have a total of $51 per unit, including a $10 charge for soldering, assembly, packaging, and accessories. Our marketing strategy focuses on partnering with school districts for bulk orders of our glasses, integrating them into programs for visually impaired students. We will reach out to special education departments with free trials and present at education conferences. To promote adoption, we'll offer tiered discounts for orders of 50 or more units and assist districts in applying for grants from the government. Additionally, we plan on collaborating with state education departments to secure funding and establish our glasses as a standard accessibility tool in schools.
Thank you.